Hello. So in this video, we're going to talk about some very specific calculations involving acids and bases reacting together in what's called a titration. So you've already covered acid-base titrations in the previous course, General Chemistry 1, generally with the reaction of a strong acid with a strong base. That's usually how it's dealt with in that course. But in this particular discussion, we're going to go into the calculations of pH for these types of reactions. Now, one of the challenging things about these calculations is that we look not just at strong acids reacting with strong bases, but we also look at strong acids reacting with weak bases or strong bases reacting with weak acids. So we have a variety of different combinations that can occur. So let me list them here just so that you can get them kind of straight. We can look at the reaction of a strong acid. An example of a strong acid would be something like HCl, right? Hydrochloric acid. And we can react that with a strong base. An example of that would be sodium hydroxide. Okay. Now, when those two react, you're going to get a double displacement reaction. So you'll get a salt and you'll get water. Okay. So that's the reaction of a strong acid with a strong base. What we'll do in these calculations is we'll look at the pH calculation for that type of problem. The next type of combination we could do is we could have a strong acid with a weak base. And this is a common type of reaction as well. So for example, let's pick a different strong acid. Let's take, for example, nitric acid, HNO3. And we could combine that with a weak base. The typical example of a weak base is ammonia, NH3. That's just a common one that people use. And notice with this one, we don't get a salt. We get the ammonium ion, and then we also have the nitrate ion. Right. So in a sense, when we're dealing with a weak base, we're dealing with a nitrogenous weak base, one that has nitrogen. Ammonia being an example, you tend to get it's a Bronsted-Lowry reaction, right? The transfer of proton from the acid to the base. So that's the second type of combination that we would deal with. A third would be to have a weak acid and react that with a strong base. See, we're just going through all the possible combinations. So for that particular reaction, an example of a weak acid, well, there's many of them. We could use hydrocyanic acid, right? That's HCN. That's the acid that historically was used in gas chambers to execute people. That might react with a strong base such as potassium hydroxide, right? KOH is a strong base. And then again, when we have the hydroxide salts, typically it's a double displacement reaction. So we would have KCN, potassium cyanide, and H2O. Water and a salt, right? Just like we talked about with the first reaction. And then the fourth combination, which we're not going to look at in this course, at least not in terms of doing the calculations here, is a weak acid with a weak base. So this is a fourth type of reaction that could occur. And again, just to come back to examples, we could have HCN, for example, reacting with ammonia. Okay, and so we would get ammonium and cyanide. Again, we're going to treat that reaction as a Bronsted-Lowry reaction where we're transferring a proton from the acid to the base. So really, it's these first three that we're going to look at here. And let's do a little bit of a review about what a titration is before we actually do any of the calculations. If you feel confident in what a titration is, you can move forward in the video and start looking at the calculations. So remember, in a titration, we typically use a device called a burette, right? A burette is a long glass tube, which is graduated. It has lines etched into it, which are calibrated, measured in a factory for volume content, right? And then the burette is the device that we use to transfer liquid to some sort of reaction vessel. I'm running out of room down here, sorry. But this is a burette up here. And then this is some sort of reaction flask. Okay. So typically we put one of the reactants in the reaction flask, and we put the other one in the burette. Okay. So for example, we might put sodium hydroxide solution in the burette, and then we might put hydrochloric acid solution in the reaction flask. And the thing about the burette is that it has a valve, a movable valve, and we can control that valve by rotating this little lever. And we can control it and add 1 drop at a time of the acid, or the base in this case, from the burette into the reaction flask. And so typically, this is a known concentration. And what's in the flask is typically an unknown concentration. But for the calculations that we're going to be doing, they're known, both are known concentrations. And by knowing both of their concentrations, that will allow us to calculate the pH of the solution. Okay. So here's what will often happen as you add more and more of, sorry, I'm having a little problem with my pen here. As you add more and more of the base to the acid in this solution, let's think about it for a moment. Before any base is added to the acid is going to be acidic, right? So what would we expect the pH to be if we have an acidic solution? Acidic solution should be less than 7, right? In fact, if it's hydrochloric acid, we can calculate the pH very easily. All we need to know is what its concentration is. The pH of 1 molar hydrochloric acid would be 0. The pH of 0.1 molar would be 1. The pH of 0.01 molar would be 2. So what we can do then is we can do certain calculations, but we can go further than that. We can actually calculate what the pH of the solution is as we add more and more of the base to the solution, to the mixture. And what should happen to that pH? If you think about it, if you're starting off as an acidic solution, but then you add some base to it, the base is going to react with some of that acid and lower the acid's concentration. If you lower the acid's concentration, the solution will be less acidic, right? So more base, less acidic. So the pH will start to increase. And that's what's observed when we do these sorts of titrations. The pH might start very low, but then it will rise as we add more and more base. Now keep in mind, we could do the opposite. We could put the base in the flask and add acid to it from the burette, right? We're just reversing the direction. If we had in the flask base initially, the solution would be basic. And as we add acid to it, it would become less and less acidic. Okay. So let's, I'm sorry, less and less basic. So let's take a look at essentially what happens. If we plot on the y-axis pH and we plot on the x-axis volume of base added, we start, I'm going to put pH 7 up here just so you can see. We start at a low pH, which depends on the concentration of the acid. But as we add base, the pH starts to rise slowly at first, but then very rapidly. It really goes almost vertically, and then it starts to slow down again. And we get something like that. And this is a very typical response curve that we get for acid-base reactions. They generally look something like this. It's often referred to as an S-shaped curve or a sigmoidal curve. It's a type of shape of a titration curve that we see when we react acids and bases. Now notice the pH started low, went up to neutral, and then kind of leveled off in the basic regime, right? Anything above that 7 is basic. So initially at the beginning, it's acidic because we only have acid in the flask. But once we reach a point where we've added enough base so that the pH is 7, it turns out that's an important point on that curve. Mathematically, the point on the curve is called the point of inflection. So it's the point where it's really at the steepest slope of that line, of that curve, but it's where essentially it's no longer in the acidic regime and now it's going into the basic regime, okay? So there's our S-shaped curve or sigmoidal shaped curve. So in the next video, what I'm gonna do is I'm gonna show you a couple of the possible calculations that we can do with these acid-base curves. And we're just going to look at very specific calculations. We're not going to calculate everything along the curve. There are actually problems where you could do that. But we're just going to look essentially at the very specific calculation, individual calculations with this. But we're going to mix it up with strong acids and strong bases and weak acids and weak bases. So that will provide quite a bit of variability. And you'll really have to analyze what's given in the problem to be able to figure out how to approach the calculation itself. So that'll be in the next video.